Damped harmonic motion. An object is in damped harmonic motion when the amplitude is determined by the function k times e to the power of negative ct. Now, as you notice, this is kind of like what we were working on a moment ago, but earlier, if you remember, the harmonic motion, or the damped, it was going through the origin, and it was making like a V, and we had these different, kind of like asymptotes, but they were limits. As you see this one, it's damped going to the right as we go on. It's kind of like what I drew earlier about oscillating. If you remember in a previous video, that's kind of what we're dealing with here. So here's a problem for us. It says a guitar string is plucked at a distance of 0.95 centimeters above its rest position and then released, causing a vibration. So to give you a picture, it's kind of like we pull up 0.95 and then let it go, and it starts to vibrate. The damping constant for the string is 1.3, and the note produced has a frequency of 200 cycles per second. Write a trigonometric function that models the motion of the string. Now this can be helpful if you have the two different equations written down. So we have this. Y equals KE. Y equals K times E, and it was to the power of negative CT. And then you would have either cosine or sine of, if you go back, it was WT, the omega T. Okay, you'd either have that or you would have cosine. So you could also have times cosine of that. Now, so how do we think through this? The guitar, it's talking about that first vibration. If you have a line kind of like this, we pull it up and we release it from up here at a height of 0.95 centimeters. And then that it's going to go down, and then what's going to happen? If you think about a string, it'll just get smaller and smaller and smaller. So the first thing we have to establish is which function are we using? Which one would start high? Well, the answer is cosine starts high, sine starts at 0. So we're not going to actually use sine here. We're going to use cosine for our formula. So this is our formula here that we're going to use for this particular problem. And not only that, we can start plugging in stuff. That K is the amplitude, which we had 0.95 for that. 0.95. And I should have put the 0 there. All right, and we have a damping constant. That's the C. They give us C of 1.3. So that would go right there. The only thing we need to find here is this. This comes from the period. Now, it says the frequency is 200 cycles per second. So every second there's 200 cycles. So to find that out, remember, this is going to be used, the B, when we had the 2 pi over B, that's how we found, and that's in the place of B right now. It's the same thing, so instead of having a B, I'll put a W. That's how we found the, what's it called? Not frequency, but the period. This says frequency. So the frequency is the reciprocal of that. So W over 2 pi is our frequency, which they say is 200. So if I wanted to get W by itself, I'm one step away. So I need to label this so you can see that this is period there. This is for frequency. We flip it for frequency. So if that's the case, the only step you need to do is you would multiply by 2 pi. So omega would equal 200 times 2 pi, which is 400 pi. So we actually have already arrived at our solution. It would be y equals 0.95 e to the power of negative 1.3 t times the cosine, that was a lousy parenthesis, of 400 pi t, where t refers to time. And that's your value. So this is kind of walking through everything I just said. You could either pause the video or you could look at it. But that's just walking you through. I was just giving you a little bit more detail. Now, let's try part B. So it now says determine the amount of time it takes for the same equation that we already had. Remember that equation? Y equals 0.95 e to the power of negative 1.3 t times the cosine of 400 pi t. Determine the amount of time it takes for the string to be damped so that it's between these two values. So here's what I'm going to do. I'm going to go over to my calculator and type in that equation. So we have 0.95 e to the power of negative 1.3. The calculator doesn't do t, it does x. So I'll do an x there, times cosine of 400 pi times x. And wow, we get something really, really crazy there. Now we want the value to be damped between negative 0.38 and 0.38. So here's how I'm going to do this. First, I'm going to zoom in a little bit here. Analyze, window zoom, and I'm going to zoom in. And now, we want the values to be damped between negative 0.38 and 0.38. So where would those occur? Well, if I go tab here and I type in, sorry, my calculator is going crazy here. If I type in 0.38 and negative 0.38, we should be able to see the values. So we're looking for how much time has to occur that the values are in between. And it looks like to me it's around in here. So I'm going to go menu, analyze graph, and see where they intersect. So we'll go this one and this one. And I'm looking, where's the first intersection? It appears to be right there. Whoops, it's crazy that it didn't include it. Let me try that again. Menu, analyze graph, intersection between graph here and here. And I want to see where do they first cross. Oh, it's crossed in a few places. There's one. And you could do the same here. Analyze graph. And I'm going to look for the intersection between this one and this one. And it looks like the first intersection occurs right there. So these would be the values that would be between. It looks to be about 0.7 of a second. Now again, if you wanted to, you could zoom in further once you had the spots and see just precisely kind of when it gets to those values, and you'll see that it is about 0.7, that these are about the times where it starts approaching it within. So if you rounded, I lost this point, I know I did, but it would be between about 0.7 seconds is when we finally get the value. So I'll put t equals 0.7, and this is in seconds. So here's a zoomed in portion from their old graph, and they're saying the same thing, 0.7, they just have a different value. So now you can try this one.